some points they're hitting each other out of phase, in which case you're getting a smaller wave. Now you can imagine the complexity that this causes when the actual signal is received at the other end. But 11N takes this ability for the phases to actually join together to do some of its fancy tricks with improving data throughput and data stability and reliability of data throughput. Okay, sorry if that was complicated. It started to complicate me, confuse me towards the end, so let's try some simpler stuff. Let's go over exactly what this MIMO stuff is. Now, what MIMO means is multiple in, multiple out. What it basically means is that you use multiple transmitters, each with a separate antenna, and multiple receivers, each with a separate antenna. So if you can imagine, transmitter 1, in this simple example, is actually sending out a signal which can be picked up by 2 receivers, and transmitter 2 is sending out a signal which yet again can be picked up by both receivers. And you can tell, obviously, take this to extreme. You could have a device which, for example, had 3 transmitters and 2 receivers, or even 4 transmitters and 4 receivers. So what this is doing is its ability to actually send the same stream out through multiple transmitters and receive it on multiple receivers. Now, the ability to do this is important when it actually comes to playing around with the phases. Because if you've got multiple receivers, that allows you to receive the signals at this receiver and this receiver, and you can compare the difference between the two and use that as a tool for analyzing the phase shifts that's occurred in the waves. Don't worry if it gets too complicated. Now, let's just make this, give you a simple example of what MIMO can do. Now, one thing MIMO can do is a thing called spatial multiplexing. Now, what spatial multiplexing does is it takes the single stream of data, and this is what a normal 11G single stream data type feature would be. You've got the data here, and it just goes along a single stream to hit the receiver. Now, with spatial multiplexing, using MIMO technology, what the MIMO device can do is, so this is a 2 transmitter device, is it can break the signal into 2 separate streams. It sends half by one stream, it sends half by the other stream. Now, each of these streams is going by a slightly different route. Not intentionally, that's just the way things are inside buildings. It's reflecting and scattering off the walls, so naturally each stream is going to go via a slightly different route to reach the destination. At the destination, what happens is the receiver picks up these 2 streams, and it can identify them by the fact that by looking at their phases. So it knows that this stream is different from this stream. And then by using some amazing DSP processor technology on it, it can actually take these 2 streams together to produce a single data stream within the object, within the receiver. So what we've done here is, because we've sent half the signal this way and half the signal that way, we've actually doubled the throughput. So by doing spatial multiplexing, the 11N or MIMO technology is automatically doubling the data throughput available. Oh, didn't know there was a little video showing this. Oh, that's good, isn't it? Oh, yeah, amazing. All right, let's go to the next show. Now, the other thing that MIMO can do is this thing called Spacetime block coding, STBC. What it basically is, it's similar to the previous one. It's yet again, it's got 2 streams, or multiple streams. This is a 2-stream example we've got here. But what it does this time is it actually sends the same stream over the 2 different routes, or the n different routes, depending upon how many MIMO channels it's running. So what this does is it doesn't actually improve the net throughput, but because the 2 streams are going by different routes and are perceived at this point as 2 separate streams, then the receiver can actually combine the 2 for better data reliability. So it can actually look at the 2 and fill in the gaps that are missing. So if there's something missing from this stream, it can look at this stream and fill in the missing gaps in the data. So what this does is it doesn't give you an increase in throughput. What it gives you is a more reliable throughput. Ah, you like this one. This is a complicated one. Now going back to the start, I said that you can have waves which are in phase or out of phase, and any combination between the two. Now, if you consider there were two waves leaving this transmitter here, arriving at the receiver, and the two waves were exactly in sync, so the troughs all lined up and the peaks all lined up. Now, if you were to draw a line through the peaks, you could see that the peaks are going out exactly perpendicular to the source. So they're going in a straight line. Now, what would happen if you were to actually send the second wave slightly delayed with respect to the first wave? Well, what happens then is if you draw a line through the peaks, you'll see that the incident line actually is at an angle now. So what you've actually done is you've actually steered the signal. So instead of going that way, if you actually draw a straight line down here, it's actually going this way. So if I draw some more peaks on here, you can see how it gets a bit more. So let's draw a whole pile of these waves coming out from the transmitters. Each one has been shifted slightly out of phase with respect to the previous one. So that way we've got a wavefront here, which instead of going straight across, is now actually going at an angle. So it's actually, by using this beamforming technique, it's being able to guide or aim the signal. No, I didn't want to do that. So the signal now is actually being aimed here. Now this is called transmit beamforming. It's the same system in principle that's used by modern radar systems, listening post systems, MOD systems. So rather than having the big dishes that they used to have, what they actually have is a series of transmitters and receivers on a flat panel, but each one is cunningly designed to actually alter the time delay that it actually sends its signal out. And that way it can actually steer the beam coming out, but without actually having to move the dish or flat panel. So this has actually steered the signal. Now this transmit beamforming is part of the MIMO 11N specification, but as far as I know, I don't know of any products that actually do this feature yet. It's one of those things that's in the specification. Hopefully one day it'll happen. But you can imagine if you've got this ability, your transmitter will be able to look at, be able to judge exactly which direction to send its signal in order to get the most reliable and fastest data link. Now, I briefly mentioned at the beginning that 11N technology could use 40 meg wide channels. Now, just to explain this further, the typical 11BG 2.4 to 2.5 gig spectrum actually uses 22 meg wide channels, and here we've got a little picture showing the various channels laid out, and as you can see, there's a high degree of overlap with the channels. In fact, a considerable degree of overlap with the channels. You can see this yellow one, for example, here is actually overlapping that blue one there, that green one there, that red one there, as well as that one, and just touching on this one, and it's overlapping that one. So the amount of overlap on the channels in the 2.4 gig region is quite considerable. And in practice, that means that the 2.4 gig region really only has 3 free channels to use. Now, let's take that a stage further. Let's say you wanted a 40 meg wide channel. We'll just look at the number of channels that you're going to occupy by a single 40 meg transmission. You're essentially going to take out over half the 2.4 gig spectrum by one 40 meg channel. And the problem with this is it effectively means that for 11N technology to work properly, it won't in 2.4 gig. It'll try its best, and it will use some of its tricks to actually improve things in 2.4 gig technology, but the special features it's got, which take advantage of the 40 meg, just can't work properly. So to try and summarize that, 11BG, you've got the 20 meg wide channels. Here are the channel numbers written down and the center frequency of the channels, which, as I say, in practice means you've only got 4 20 meg wide channels. In the 11N, with 40 meg